I'm Nina Zumel from WinVector LLC, and today I'm talking about squeezing the most utility from your machine learning and AI models. Let's imagine that you're in a sales scenario. From a large pool of prospects, you want to identify and contact the most promising customers. Conversions are fairly rare, so out of a pool of 10,000 prospects, you'd expect around 100 conversions if you contacted them all. Your goal is to develop a decision process for selecting which prospects to contact, based on demographic and other data, in order to maximize booked net revenue. Your data science team builds a model to predict the probability that a given prospect will convert, based on certain demographic and other characteristics. You also have gathered an evaluation set of historical prospects, and here we show how the model scores the subjects in that set, grouped by whether or not they converted. The green distribution shows the scores of prospects who converted, while the orange shows the scores of prospects who did not convert. As desired, prospects who convert tend to score higher than prospects who do not, although there is still substantial overlap. In order to use this model on future prospects, you also need to pick a threshold. If a prospect scores higher than the threshold that you picked, then contact them. Otherwise, don't. Higher thresholds result in fewer calls, but a higher success rate. A much higher fraction of prospects called will convert. Lower thresholds result in more calls and potentially a higher count of conversions, but your success rate will be lower because you will also be calling more prospects who don't convert. How do you find the best threshold to balance making sales without wasting too many resources contacting prospects who won't convert? And once you've found the best threshold for a given model, how do you know if the resulting decision policy will meet business goals? You might naturally want to evaluate models and pick decision thresholds based on machine learning accuracy metrics like sensitivity and specificity, or precision and recall. But those metrics aren't ideal from a business point of view. The reason we build models is to help our organization make decisions that run the operation. And the best model in the world is useless if the operation isn't improving. Machine learning accuracy metrics aren't always easy to map to operational goals. So, we're going to look at another way to pick thresholds, using utility. By utility, we mean that you assign rewards and costs to a model's correct and incorrect classifications. In general, a different cost or reward to true positives, false positives, and so on. Basically, utility expresses how much it costs when you make a mistake or when you miss an opportunity. Since in an organization these costs and rewards tend to be in monetary units, like dollars, utility is a good way to express how useful a model is with respect to organizational goals. And it provides a useful language for data scientists to communicate with their business partners about project goals and model performance requirements. Let's go back to our sales example. You have a model that scores prospective customers on likelihood of conversion, and you expect about a 1% conversion rate. You need to set a threshold score for deciding which customers to call. Let's do a utility calculation to set that threshold. It costs $5 to contact each prospect, so you don't want to waste resources calling prospects who are unlikely to convert. Every conversion is worth on average $100, so you'd like to not miss any potential conversions. The goal is to strike a proper balance in order to maximize booked net revenue. Let's assign values to each possible outcome. True positive classifications are prospects that are contacted and convert. They bring in $100 on average, minus the cost of contacting them, so we will value them at $95. False positive classifications are contacted prospects who don't convert. They cost $5 for the call. Prospects you don't contact don't cost you anything and don't earn you anything. So you can say both true negatives and false negatives have a value of 0. Or you could express the idea that false negatives represent customers that actually wanted your good or service, and hence might go to your competitor instead if you don't contact them. To capture that, let's express a small penalty on missed conversions by giving the false negatives a value of -1 cent. Once you've assigned values to the different types of classifications, you can use those values to measure the utility of a classification rule or threshold over an entire population sample. Here, we're representing all the prospects in the evaluation set, sorted by model score and whether or not they converted. Any given threshold partitions the prospects into those classified as negatives, or do not calls, and positives, or those to be contacted. Since this is an evaluation set, we know which classifications are true, or correct, and which are false, or incorrect. Now we can assign each outcome a value according to our utilities. The total utility realized over this population by this classification rule is the sum of all of the individual utilities. The optimal threshold is the one that maximizes total expected utility. As an exercise, you might want to estimate the range of reachable utilities for this data by evaluating it with 3 ideal models: an overeager model, where you contact everyone; a do-nothing model where you contact no one, and a crystal ball model that identifies exactly the people who convert and no one else. The total value of calling everyone is large and negative because the cost of contacting the entire population outweighs the value of the sales that you make. With the current set of utilities, calling no one still costs you $1.06, representing the 106 customers who might instead go to your competitor. The crystal ball model brings in $10,070. This maximum achievable revenue gives you an ideal value against which to compare actual model performance. Here is a plot of total utility for the current customer scoring model and evaluation set. The y-axis gives the total expected utility for a given threshold, as the threshold is swept from a 1.5% chance of conversion, according to the model, to a 5% chance of conversion. The break-even point is to call everyone with more than a 1.7% probability of converting. At that threshold, you make enough sales to exactly cover the cost of calling all the targeted prospects. Using a lower threshold would lose you money because you would be contacting too many people who don't convert. The optimum threshold is about 2.17%. At this threshold, you contact 427 people out of 10,000, or about 4% of the total set of prospects. From those 427 contacts, you make 42 sales out of 106 possible, and the total utility of this optimal decision rule is $2,064. This is about 20.5% of the total achievable value of $10,070. Is this performance good enough? Maybe, maybe not. The point is that you now have a concrete number, or a set of concrete numbers, to help you decide if this model is good enough to meet your business targets. If it is, you're good to go. If not, then you have to spend more time building a better scoring model. An important takeaway here is that how well a model performs for your organization doesn't just depend on the model itself, but also on organizational goals and on the relative value of correct and incorrect decisions. Let's see how a change in goals and utilities affects how a model is used. Let's take the model and evaluation data that we've been using, but this time we'll interpret the model as a screening test for a rare but serious condition. This condition affects about 1% of the population of interest. The evaluation set is a set of subjects from this population, along with the medical information about them that drives our model. We apply the model to all the subjects in the evaluation set as the initial screening for this medical condition. Let's say that the screening test costs $10. If a subject tests positive, then we give them a more expensive but more accurate follow-up test, which costs $50. If we catch the condition early, then it costs $1,000 to treat and, let's say, cure them. But if we miss a case and don't treat the patient until the condition gets worse, then the cost of that late treatment is much larger than an early intervention would have been, say $10,000. The goal in setting the threshold for the initial screening test is to minimize overall total cost. Now let's turn these costs into utilities. The true negative classifications are subjects who are tested and correctly screened negative. They cost the price of the test, or $10. If a subject tests positive on the initial screen, they are given a follow-up test, which costs $50. Those who correctly screen negative on the follow-up test are false positive classifications with respect to the initial screen. The total cost for a false positive subject is $60. True positive classifications are those subjects who test positive on the initial screening and actually have the disease. Because these subjects were caught early, their treatment costs $1,000. The treatment, plus the price of the two tests, gives a total cost of $1,060. And finally, false negative classifications are those unlucky subjects who tested negative on the initial screening, but actually had the condition. Because they were caught late, they eventually get the more expensive late treatment. So this is an example of a problem where all the utilities are negative, but we still want to maximize value by minimizing costs. In this situation, the optimal threshold would be to follow up with everyone with more than a 1.06% probability of having the disease. This comes to 37% of the population. The good news is that this screening finds 95 of the 106 people in the population with the condition. The bad news is that it misses 11 of them. The total cost of this policy is somewhat under $500,000, $490,200 to be exact, which is about 2.3 times the lowest possible cost of $211,300, which is what it would cost if there existed a magic early screening test that detected exactly the subjects with the condition, and only them. One of the advantages of using a utility formulation to evaluate model and decision policies is that it allows stakeholders to experiment with different goals and scenarios. For example, suppose you wanted to consider a threshold low enough to catch everyone in this population with this medical condition using the early screening test. This would require halving the decision threshold down to about a 0.5% probability of having the disease. This threshold would assign a follow-up test to about 75% of the population. In other words, for this population of 10,000 subjects, over 7,500 of them would need to take a follow-up test in order to winnow down to the 106 subjects who have the condition. The cost of follow-up screening the false positives alone would come to about $488,000, and the total cost of the policy would be $584,750. Which threshold to choose is a matter of policy and priorities, not data science. But a utility formulation gives decision makers a tool to discuss the pros and cons of each scenario. So we've seen that even with identical models, the best threshold changes radically depending on the operational goals. Here's the distribution of model scores again, with the threshold for the sales example in pink and the medical example in purple. You can see that the medical domain prioritizes identifying as many true positives as possible, or, as it's called in medical statistics terminology, high sensitivity, over a low false positive rate, because false negatives are far more expensive than false positives. The sales domain prefers a higher success rate, or as it's called in information retrieval terms, high precision, because too many false positives will generate too high an expense relative to the revenue brought in. The above examples demonstrate that models with similar accuracy characteristics can be used or evaluated different ways, depending on the utilities and goals of the specific use case. In this discussion, we've seen that machine learning accuracy metrics in and of themselves don't always express how, or even if, a model can meet an organization's operational goals. Utilities, on the other hand, express model performance in more operational units, like money. This allows one to quantify the trade-offs between false positives and missed opportunities in a way that makes sense to the business. Hence, utilities can be a more intuitive way to elicit performance goals from stakeholders and business partners. If you are interested in exploring how you might use utilities in evaluating machine learning models or setting business policy, please reach out to us at WinVector LLC for training or consulting. Thank you.